Hi everyone, this is our first lesson for Math 146. And I'm going to start off, our first lesson is going to be on ratios, variation, and proportions. So a ratio is simply just comparing relative values of numbers or a given quantity. And you might see it or you might hear it in different ways. So you might see something shown as 5 to 2. Or 5 parts to 2 parts, okay? Or if you use a colon, okay? So 5:2. A common fraction, this could also be written as 5 divided by 2. Or you can even see them where they're fully calculated out. So 5 divided by 2, you could actually put that in your calculator and get 2.5, okay? Or in some instances where it's actually a percentage, you might see this as 250%. In other words, this part, 5, is 250% larger than the other part, which is 2. Okay, so all of those are ways to write a ratio. Okay, because what you're doing is you're comparing two things, or in some instances, you could write a longer ratio that compares 3, 4, 5 items. Okay, so ratios are typically comparing quantities of the same type or same unit of measure. Okay, so when you have ratios, they're usually just written as a simple fraction, let's say 5 divided by 2, with no units. All right, and the examples of that would be the same unit of measure. In this case, if it's weights, you might have 5 kilograms to 2 kilograms, and that can be written as 5 divided by 2. If you have distances, okay, so let's say you're traveling, or let's say you have a slope of something and it slopes 10 meters for every 1 kilometer. Okay, if you do that, you have to leave it as 10 meters per kilometer. But if the units were the same, okay, so in this case, you can convert a kilometer to meters. Well, 1 kilometer is equal to 1,000 meters. Okay, so we can actually convert using ratios as well. So if we wanted to convert, all right, we can multiply it by 1 kilometer divided by 1,000 meters. The reason for that is this is considered a ratio, okay? 1 kilometer to 1,000 meters. So if you do that, you'd have units that canceled. So what you're left with in this is 10 divided by 1,000, which is equal to 0.01. All right, so all I did there, okay, was I used ratios to actually convert, okay? And what you see is you end up with something that's unitless, and that's because all of the units have canceled out in this question. You could take that a step further, remember from our last slide, and it can be expressed as a percentage. So you could take the 0.01 and multiply it by 100%, okay? So that means 1%, okay? All of those are still considered ratios, and they're unitless, okay? Because they're comparing two elements of the same type or same unit of measure. Now, if we had left it like this, 10 meters per kilometer, okay? They have different units, so that would be considered a rate, okay? A good example of that is if you look in your car or truck on your speedometer. It's given the speed you're traveling in either kilometers per hour, which is what we are used to here in Canada, or usually on the interior portion of your speedometer dial, there's smaller numbers, and those numbers are actually miles per hour, or abbreviated as MTH. Okay, those are all ratios. Okay, and it's the ratio of the amount, the distance you expect to travel within a certain period. When its speed is within an hour. Okay, so both kilometers per hour and miles per hour are both comparing on a per hour basis. So in this case, because the units did not cancel, you have to keep them when you're writing your answer. In other words, 40 kilometers per hour. Okay, and that's because without that, if this was just written as 40, then there's no context. 40 what? Is it 40 miles per hour, kilometers per hour, inches per second, meters per second? It could be any number of units in this case. So when you're looking at rates, make sure you keep the units listed. Okay, so using what we know about ratios and rates, let's look at an example problem. The percent grade of a road is the ratio of vertical rise to horizontal change in distance expressed as a percent. The highway rises 75 meters for each 1.2 kilometers along the horizontal. What is the percent grade? Okay, so basically, this is looking at a roadway. Okay, so if you've got a horizontal distance of 1.2 kilometers, okay, it'll rise a certain portion, in this case 75 meters. And a lot of instances why that could happen, if it's a smaller density means the side of the road, it will slope. Okay, so water will tend to flow away from it. Okay, so flowing off the road, or snow melt accumulation or snow accumulation, as an example, is where you might see this being used. So a lot of times it's shown as a percentage, right? So it's a percentage of grade. So there's two types of things we have to combine together in this formula. First is to figure out what the ratio is. In this case, in the question it says it's the vertical rise. And then when you see the words to the horizontal change in distance, remember that is the same as writing divided by the horizontal change in distance. Remember, when we showed ratios, you could write it as 5 to 2, which is the same as 5 divided by 2. So all I've done is you look at this wording that says 2, and you know that you can write it as a fraction. Okay, so that was step one. That's determining our ratio that we're trying to find. So that's actually equal to the percent grade. The last item we have to add is we want it to be expressed as a percent. So remember from my previous slide, in order to convert something to a percentage, you can simply multiply by 100%. Okay? So that's just kind of piecing together the formula and the ratio based on the information provided in the question. So that would be equal to the percent grade. Okay? So keep in mind, we can now just substitute our values in. Okay, so we've got our vertical rise, 75 meters, divided by our horizontal change in distance, 1.2 kilometers, and that's multiplied by 100%. Now, what you notice here is the units are not the same. Meters and kilometers are not the same measure of distance. So if we left it like this, we wouldn't be showing our answer as a percentage, right? Because we would have to keep meters and kilometers in this. Okay, we wouldn't just have percentage. So that means we have to convert either meters or kilometers to the same units. In other words, they're both in meters or they're both in kilometers in order to be able to actually find a percent grade, right? Because we don't really, the percent grade is just a percentage, right? It doesn't matter if it's in meters, it doesn't matter if it's in kilometers, okay? It's just a percentage. So I'm going to choose to convert kilometers. So remember, again, from our previous slide, we can convert it by multiplying it by another ratio that's equivalent, okay? So 1.2 kilometers, okay? If we're converting to meters, we can multiply it by a ratio of meters to kilometers. So for 1 kilometer, there's 1,000 meters divided by 1 kilometer. Okay? So in other words, there's 1,000 meters in a kilometer. So now with the same units on the numerator and the denominator, in this case both kilometers, the kilometers cancel, and we're left with 1,200 kilometers. So we can substitute that value in. 1,200 meters. Okay, see, all of us can make these types of mistakes. So we can substitute that value in. So that's the same as 75 meters divided by 1,200 meters multiplied by 100%. So in this case, because we have the same unit of measure, meters and meters, they cancel. So 75 divided by 1,200 would give you 0.0625 multiplied by 100%. So that gives you a percent grade of 6.25%. Okay, so this question kind of takes all of these lessons that we've learned in the last 2 slides into one type of question. So now when you look at ratios, you can also look at proportions. And what proportions are is simply 2 ratios that are equal to each other. Okay, a great example of this is fractions. Okay, so when you talk about equivalent fractions, 2 divided by 4 and 1 divided by 2 are equal. If you place both those numbers in your calculator, you will get 0.5. Okay, those are also known as equivalent fractions, but they're also said to be proportional to each other. So we'll see why that's important in later lessons of this unit when we talk about items like similar triangles. Okay, the other area where you see them used a lot is when you're scaling, and when you're either scaling on a set of design drawings for a piece of mechanical equipment, or you're looking at a survey drawing, okay, and it's drawn to a certain scale. So oftentimes on those drawings, you may see a scale. So on Google Maps, you might see a scale that says 0 and 20 meters, meaning this distance on the map is equal to 20 meters in real life. Okay, so that is known as a scale, and scales rely on this principle of proportion. Okay, so you're finding a proportional distance, okay, looking at a small scale map, right? A small scale map, for example, from Sault Ste. Marie to another city in Canada. So using proportions, I'm going to give you an example. This is from Google Maps. And given the measurements in the image below, what is the approximate distance between Sault Ste. Marie and Sudbury? So you'll notice I've given you 2 measurements here. One is a straight line, okay, directly from Sault Ste. Marie to Sudbury. Now realize that the actual path, okay, is here in yellow, taking the highway. This is purely direct distance to and from. The second item that I gave you here, okay, is Google gives you a scale. So what it's saying is this distance on the map is 20 kilometers. So I've measured that for you and provided it as 1.5 centimeters. So using the scale and using the actual line between Sault Ste. Marie and Sudbury, we can set up 2 ratios that are equivalent to each other because this is a scaled map. Okay, so the map is drawn to scale. So what you have is you start with the same ratio. A divided by B has to equal C divided by D. Okay, one ratio will be the actual scale on the drawings. The other ratio, okay, will include the distance you'd actually have to travel and the measurement on the map from Sault Ste. Marie to Sudbury. Okay, so your first ratio, to go 20 kilometers, it is 1.5 centimeters, centimeters on the map. Okay, so that is your first ratio. Your second ratio is you don't know the distance, so the numerator can just stay as the letter C. You don't know the actual kilometers, but what you do know is is the actual measured distance on the map, because again, this is to scale, and it's 19.95 centimeters. So now simply to solve for that, okay, notice I've left the units, because again, these aren't all the same units. You'll see why that's important. To solve for this, I need to have C by itself. So to do that, I need to multiply both sides by 19.95 centimeters. What that does, okay, is on the right side, the 19.95s is in the numerator and the denominator, and it cancels, as well as the centimeter units. On the left side, just the centimeter units here cancel. So the only units we have left are kilometers. So if you multiply that out, you end up with a value of C, and that's going to be equal to 19.95 times 20 divided by 1.5, which is approximately 266 kilometers. Okay, so this is an actual example where you may not think of it this way, but what it is you're using proportions to actually use a scale properly on whether it's a map or a drawing. So after talking about ratios and proportions, okay, where those were measuring kind of a proportion from one to the other, right? So 5 to 2 was the example I have been using throughout this lesson. And that can be also written as 5 parts to 2 parts of something. Okay, so the next concept is something similar. It's called direct variation. So I'm going to talk about direct and inverse variation as the last 2 items in this lesson. So variation is when you're directly comparing 2 or more quantities and variables. Okay, in this case, I've called them one variable x and one variable y. Okay, so if you have a ratio and they're directly related to one another, okay, in other words, y and x are directly related, they're said to be proportional. So what that means is that there's a certain number that you can multiply one of those by to obtain the other every single time, okay? And we call that number k. So in other words, your one variable y is equal to k, or some number, multiplied by x. When we have this, we say that y varies directly with x. Okay, you can say it's directly proportional to x or just proportional to x. Okay, and what this means is that as y increases, that means x would increase, and as y decreases, x would decrease. Okay, so on a graph with the y-axis up and down and the x-axis left to right, the graph would look like a straight line trending upwards. Okay, and the reason for that is as you increase x, your y should increase, and vice versa. Okay, in this case, to the right is positive in the x-axis, and up is positive in the y-axis. That's known as a Cartesian coordinate system. So what we usually want to find out when it's proportional is usually your first step is you solve for this constant k, because it's not going to change. Okay? Another example of that is when you look at springs. Okay? Some springs are easy to push in and out or compress. Some springs are more difficult. And that is affected by what's known as their spring constant, coincidentally usually referred to by the letter k as well. Okay, and that's because that force varies directly proportional to what that spring constant is. Okay, the stronger the spring, the higher that constant is. All right. So let's look at an example. Okay. Weirdly enough, or oddly enough, I've planned it so that it's a spring question. Hooke's law states that the force needed to stretch a spring is proportional to the amount the spring is stretched, and we're calling that E. if 10 newtons stretches a certain spring 4 centimeters, how much will the string be stretched by a force of 6 newtons? Okay, so your first step is you have to set up your equation. Okay, so I'm going to say, okay, the force is F, and it's proportional, all right, to the amount that the spring is stretched. Okay, in other words, the more it's stretched, okay, the more force you would need to apply. So I'm going to call our constant here K, just like I did in the past, all right? And I'll start with just our basic equation. If it's directly proportional, y is equal to K times X. Y, in this case, I will call our force, okay, F, and that's equal to K times X, or in this case, the amount the spring is stretched, times E. Okay, all I've done is replace y and x with the appropriate letter values given in the question. So the question gives you a force, and it gives you the amount the spring stretches. And this is usually the case. And the reason for that is it allows you to substitute those two values into this equation. And the only unknown that will be left will be the spring constant, K. Right? So you can use that to solve for K. And we'll see what that does. Okay? So your force was 10 newtons. And that's equal to K multiplied by 4 centimeters. So to solve, okay, for K, we need to divide both sides by 4 centimeters. What that does is it cancels the 4s and the units, centimeters, on the right side. On the left side, the units don't cancel. So what it becomes is 10 divided by 4, which is 2.5 newtons per centimeter, is equal to K. Again, this is a rate, right? Because the units are not the same. So we have to keep the units in this question. So that's equal to K, which in this case, you can call it the spring constant. So what that does is it now creates an equation for us. The force is equal to 2.5 times E, or the amount the spring is stretched. So now we can answer the second piece of that question, or you could actually take any force profile for this spring, not just 6 newtons, and figure out how much it would correspondingly stretch. Okay, that's the purpose of creating this equation at the start. So to answer the question, our force is 6 newtons, so we substitute that in, and that's equal to 2.5 times E, the amount the spring is stretched. So now to solve for E, we have to divide both sides by 2.5. Okay? So on the right side, the 2.5's cancel. And what we're left with is E is equal to 6 divided by 2.5, or 2.4 centimeters. What I didn't show you here, okay, and I should have, is what this actually was 6 newtons is equal to 2.5 newtons per centimeter multiplied by E. So when we divided both sides by 2.5 newtons per centimeter, the newtons per centimeter and the 2.5s canceled on the right-hand side, and on the left side, just the newtons canceled. So we were left with just a unit of centimeters. Okay? So our final answer came out as 2.4 centimeters. And you can see that that number in your head makes sense, right? You applied a greater force when you were calculating the constant, and it stretched 4 centimeters. So when you apply less of a force, it should be stretched less. Okay. Okay, let's look at a second example. the amount of heat H required to melt ice is proportional to the mass of ice that is melted. If it takes 293,000 joules to melt 875 grams of ice, how much heat is required to melt 625 grams? Okay, so again, we're seeing that the amount of heat, they're calling H, is proportional to the mass of M of the ice that's melted. Okay, so knowing that, we can start with our base formula, y equals kx. In this case, the heat, H, is proportional to mass, so heat is the y variable, so H is equal to K times M, okay, which is the mass. So now, knowing or having the data on one instance, we can substitute that in to figure out the constant, okay? So in other words, H, 293,000 joules, is equal to K times 875 grams, okay? The mass of ice. So to solve for this, we can now divide both sides by 875 grams. Okay, so we can get K by itself. On the right side, the 875 and the grams units cancel. So we're left with K is equal to the 293,000 joules divided by the 875 grams. And what that comes out to is 334.86 joules per gram. Again, we can't cancel those units out because they're not the same. Okay? So our equation becomes H is equal to 334.86 multiplied by M. Okay? So now, knowing our constant, we can figure out the heat for a different amount of ice. So H is equal to 334.86 joules per gram multiplied by 625 grams. Okay, again, grams is in the numerator and the denominator, so we can cancel it, and we're left with just joules. Okay, that makes sense because our heat output will be in joules. So 334.86 times 625 gives you a heat value of 209,287 joules. Okay, you'll notice it's a little different compared to my answer, and that's just because of rounding. Okay, so if you didn't round your initial K value and you kept it with more decimal places, when you do this question yourself, you'll see that you'll get a slightly different answer. If you do have that question in a test, if your answer is off by a small amount like this, it isn't something that I would mark you wrong for. Okay, so don't worry about that. So looking at the opposite direction, the second item I want to talk about is called inverse variation. Okay, so direct variation was where they were directly proportional to each other. In other words, the equation was y equals kx, k being some constant, and as one variable increased, the other increased as well. Inverse variation is in effect the opposite of that. So instead of being y equals k multiplied by x, it's y equals k divided by x. This is called inverse proportionality. So as y increases, x would have to decrease, and vice versa. If x gets larger, if this denominator gets larger, then k is being divided by a larger number. So your value of y would in effect get smaller. So they have an opposite relation. And the graph of that reflects that. Okay, so the previous one showed a graph continually increasing as x and y increases. What this shows is in effect the opposite. As x increases, you can see y from one point to the next going down. And similarly, as y increases, you can see x going down or getting smaller. Okay, So a couple popular ways you might hear this being said. Y is inversely proportional to X, or Y varies inversely with X. Okay? So in this instance and the last instance, okay, we used in direct variation y equals kx. In inverse variation, y equals k divided by x. Okay? So in these cases, we're both assuming it's just a term x. But these still apply regardless of what it is. It could be inversely proportional to the square of another item. In other words, y equals k divided by x squared, or y equals kx squared. Or similarly, it could be something like it varies directly with the square root of another item, or y equals k times the square root of x, or y equals k divided by the square root of x, okay, depending on if it's direct or inverse. Okay, so the reason I'm telling you that is it isn't just something multiplied by x, and that is something that's provided in the question. It'll say that it varies with the square of this term or the square root, okay, and whether it's proportional or inversely proportional. So what becomes important is that you read the question and figure out what terms are being noted, okay? So let's look at an example. The time t required to empty a wastewater holding tank is inversely proportional to the cross-sectional area A of the drainage pipe. If it takes 2 hours to empty a tank with a drainage pipe for which area A equals 48 centimeters squared, or the area, how long will it take to empty the tank if A equals 68 centimeters squared? So again, a couple items to notice. If you start with our equation, y equals k over x, you'll notice that the first term, time t, is inversely proportional to a. So we can substitute those values in. Time t is equal to k, some constant, divided by the cross-sectional area a. In other words, as the area of your pipe becomes larger, it takes less time to empty the tank. Thinking about that logically, okay, that makes sense. The bigger the pipe, the more water, the more fluids that can flow through it. So now that we have our equation written, and again, it just says it's inversely proportional to the area. It doesn't say the square of the area, the cube of the area, the square root of the area, it just says area. So we can assume that it's just A, okay? So knowing this first set of data points, 2 hours and the cross-sectional area 48 centimeters squared, we can substitute those values in, okay? So in other words, our time, 2 hours, is equal to k divided by 48 centimeters squared. Now solving for k, all right, we have to remove the 48 centimeters squared from the right side of the equation. So you multiply both sides by 48 centimeters squared. So both the centimeters squared and the 48 cancel on the right-hand side. And our value for k is equal to 96 centimeters squared times hour, okay? Because the units are not canceled here. So you have to keep those units within your constant, okay? So our equation becomes t is equal to 96 divided by a. So our second area that we know is 68 centimeters squared. So we can now substitute that in to find the new time. So time is equal to 96 centimeters squared times hours, times hour, divided by 68 centimeters squared. So again, the centimeters squared cancel here, and we're just going to have hours as our units. So if we calculate this out, our time is equal to 1.4 hours. And again, that makes sense because the cross-sectional area is larger, so it should take less time to drain with a larger pipe. Okay, for our last example, I'm going to kind of bring all of the concepts together. The acoustical intensity I of a sound wave is proportional to the square of the pressure amplitude P and inversely proportional to the velocity V of the wave. If I equals 0.474 watts per meter squared for a pressure of 20 pascals and velocity of 346 meters per second, find I if the pressure is 15 pascals and velocity is 320 meters per second. So notice I stress the and because there's two variables that the acoustical intensity I in this question is proportional to. Okay, and you're going to see that that is common the more and more and more you see formulas throughout your program. So remember, we had two equations, y equals kx and y equals k divided by x. Okay, in this case, we have to use both. The constant k is still there, but one item is proportional and one is inversely proportional. Okay, so our y term is the same for both. All right, our y term is the intensity I, and that's equal to some constant k. That has not changed. But we have two variables here, so you can write them out, okay, basically by sounding them out in the question. Your first item is the pressure amplitude P is proportional, or the sound wave is proportional to the square of the pressure amplitude P, in other words, P squared, and inversely proportional to the velocity V. So in other words, inversely divided by V. Okay? You can sound these out when you have multiple terms that need to be added in. Okay? So all I've done is replace the variables from our base equation with the letters corresponding with this scenario. So now we can go about our business the exact same way we have done for both direct and inverse variation. We're given one data set, and that data set allows us to find the constant k. We then use that constant k now in our newfound formula with it to solve a second data set. Okay? So if I substitute everything into this equation, in the first instance, we have I is 0.474, and that's equal to k multiplied by 20 pascals squared divided by the velocity, in this case, 346 meters per second. Okay? The units will cancel. I'm not going to show you them in this example because they do get more complicated. But know that since we're using a constant in this and our units are all the same for both examples, I'm not going to show you the units here. So if we calculate this out, we get 0.474 is equal to 1.156 multiplied by k. So to solve for k, we have to divide both sides by 1.156. So we have k by itself. On the right side, the 1.156 cancels. And what we're left with is k is equal to 0.410. So now our equation becomes I is equal to 0.410 times p squared divided by v. And we have a new data set, 15 pascals and 320 meters per second. So we can solve for our new value of I. So I is equal to 0.410 multiplied by 15 squared divided by the velocity, 320 meters per second. And if you solve this, you get I is equal to 0.288. And again, our units didn't change. I didn't show you the unit cancellations, but it didn't change. So it's still going to be in watts per meter squared. Okay? So I hope you kind of noticed the thought process here. And this is very useful when you look at trying to develop an equation to describe something using just the information that you know, okay? Starting to make connections between one variable and another. So that was all I had for your first lesson. This was chapter 18 in your textbook. So I've given you some practice questions. I highly recommend that you look at these practice questions only. There's more in this textbook, but because the textbook is sequential, this is chapter 18 of the textbook, it's assuming that you've went through the first 17 chapters, which obviously we haven't covered. You've covered some of them in your previous courses, but not all of them. So I picked out specific examples that you should be able to accomplish given what we've done today. Okay, so thanks for listening and look out for my next lesson.